Continuing our discussion of the coaxial pair of solenoids, in part A we have calculated the flux through each coil of the inner solenoid, and then in part B the outer solenoid, and we found the total inductance for the total flux divided by the current, which is basically two inductors connected in series. So we have to add the inductances of these two actually. Now, in part D, what would be the inductance if the sense of the inner coil were reversed? What would be the effect of reversing the sense of this coil? Then you would have the current flowing in the same direction, which means the magnetic field due to that current would be in plus I hat direction instead of the minus I hat direction. Okay. So, if the sense of the current in the inner coil is reversed, we have B2 is equal to mu0 number of turns per unit length N2 over lambda I in plus I hat direction instead of minus I hat direction, so that the flux through each turn of the second coil, the inner solenoid, would be mu0 I divided by lambda, this time n1 plus n2 pi a squared, the area of each coil of the inner solenoid. So that would be the flux. And for R between A and B, we would have still the same magnetic field B1, which is mu0 and 1 over lambda I in I hat direction. The flux through each coil of the outer solenoid would be then mu0 and 1 divided by lambda I, the magnetic field in the region between B and A, R equals B and A, multiplied by the area. This is what we did in part B also. That's this part. Plus the flux through the second, each turn of the second solenoid, which is now mu0 I over lambda and 1 plus n2 pi a square. So this becomes mu0 I pi divided by lambda n1 b square minus n1 a square plus n1 a square plus n2 a square. So these two would cancel, and I will be left with the flux through each coil of the outer solenoid, mu0 I pi over lambda n1 b squared plus n2 a squared. Then what would be the total flux, capital Phi, total? It would be number of turns in the outer solenoid multiplied by the flux through each coil, plus number of turns in the inner solenoid multiplied by flux through each coil of the inner solenoid. So this would become mu0 I pi divided by lambda n1 phi 1, so it's n1 squared b squared, n1 squared b squared, plus n1 n2 a squared, that's this term. Now n2 n1 a squared, and then I would have n2 squared a squared for the total flux. So you can see I have N1b squared, 2N1N2a squared, and N2 squared a squared. That's the inductance times the current. So the total flux, phi total, then becomes mu 0 I pi divided by lambda N1 squared b squared plus 2N1 N2 a squared plus N2 squared a squared, which is the inductance times the current, so that the inductance becomes mu 0 pi divided by lambda N1 squared b squared plus 2N1 N2 a squared plus N2 squared a squared. Let's move on to part E. In the original configuration, what would be the inductance if lambda is 20 centimeters, A is 1 centimeters, B is 2 centimeters, and 1 is 1200, and N2 is 750? So let's list these numbers here. The length of the solenoid, lambda, is 20 centimeters, which is 0.2 meters. The radius A is 1 centimeters, which is 0.01 meters. The radius B is 2 centimeters, which is 0.02 meters. Number of turns in the outer solenoid is 1200. Number of turns in the inner solenoid is 750. The self-inductance is mu 0 pi divided by lambda. In the original configuration, N1 square b square minus N2 square a square. The answer we have found in part C. Substituting the numbers, we have 4 pi 10 to minus 7, that's mu 0. And multiplied by pi becomes 4 pi squared 10 to minus 7, divided by 0.2, multiplied by 1200 squared and 1 squared b squared, 4 10 to minus 4, minus 750 squared a squared, 1 10 to minus 4. So this gives us an inductance of 10.3 millihenry. Now, if I look at part F, using the values from part E, what would be the inductance in the configuration of part D? That's in the reverse direction. If the current is reversed in the inner solenoid, then I would have L is equal to mu 0 pi over lambda, which is 4 pi square 10 to minus 7 divided by lambda, 0.2 meters. And 1 squared, 1200 squared, b squared, 4 10 to minus 4, plus 2 and 1 and 2, 2, 1200, 750, 1 10 to minus 4, a squared, plus 750 squared and 2 squared, a squared, 1 10 to minus 4. This gives us an inductance L is equal to 16.0 millihenry. Okay, so part E and part F were basically applications of plugging in some numbers to the inductance values. And in part D, what we did was we changed the sense of the coils. So instead of the coils wound this way and the current coming down, now current is going up. So current is going up. In that case, we would have the two magnetic fields adding up inside, and that would give us basically a total magnetic field mu 0 I over lambda n1 plus n2 in I hat direction multiplied by the area of each coil. I get the flux through each coil, and in between A and B the situation doesn't change, so the total flux becomes n1 phi 1 plus n2 phi 2 because I have n1 turns in the outer solenoid and 2 turns in the inner solenoid, and that gives me the modified inductance. Now, as I said, we can think of this as two solenoids connected in series, so two inductances are adding up. So we could consider this solenoid separately and this solenoid separately and add their inductances, and that basically gives the same result. Because they're connected at the end, it's the same current flowing through two inductors in series. Okay. So in part E and F, we have substituted some numbers and found that when we change the sense of the current, the inductance increases.